Thank you. Thanks for the invitation. So yeah, today I'm going to be talking about two kinds of barriers for matrix multiplication, and specifically within this group theoretic framework. We're going to mostly think about this group theoretic framework for matrix multiplication algorithms. So in 2003, Cohn and Umans showed that some purely group theoretic question could potentially give non-trivial upper bounds on the exponent of matrix multiplication. And something that was nice about this is that people had kind of been stuck at the time for like 13 years since the Coppersmith-Winograd stuff. And this gave like a completely new perspective on things. And then shortly later, in work with Kleinberg and Peggy, they showed that in fact you can prove non-trivial upper bounds on the exponent of matrix multiplication within this framework. So this is not like some obvious fact. And what's kind of disturbing though is that the family of algorithms, all the constructions you get are sort of group theoretic analogs of the previous Coppersmith-Winograd algorithms. So this is like it seems very bizarre to me still, because I mean, the original question, it's not clear at all that you should be able to do anything with it. And then this is what you get is just, it's very mysterious to me. And what's maybe more disturbing is that it's known that these specific kinds of constructions, these Coppersmith-Winograd type constructions in this group theoretic framework are subject to barriers. So you can't prove them at equals 2 using them. And this raises the question of like, are there any other kind of non-trivial constructions in this framework? And in particular, these Coppersmith-Winograd constructions make use of highly non-simple families of groups. So a natural question would be like, in very simple groups, is there anything you can do? So just looking elsewhere for answers to this question. And so in the first part of the talk, we'll sort of have two parts. In the first part of the talk, I will discuss some joint work with Jonah Blasiak, Henry Cohn, Josh Grochow, and Chris Umans. And one thing we did in this paper is we showed that, in fact, like groups at the opposite end of the spectrum of like where the Coppersmith-Winograd stuff is happening are also subject to other kinds of barriers. And so specifically, we show that groups of Lie type cannot prove omega equals 2 in this framework. And this is closely related to this work of Gower's on quasi-randomness in groups and the existence or non-existence of large product-free subsets in groups. And I will sketch the dilemma and maybe also give full proof of it. In the second part of the talk, I'll discuss the previous barriers for fast matrix multiplication, which sort of I think about as coming from some algebraic structure of like the matrix multiplication tensor. And this is specifically we'll be talking about the existence of these things called multiplicative matchings in groups and how you can prove upper bounds on these using slice rank. And this is all very, very closely related to like the breakthrough, the capset problem. And then so you can use slice rank to prove upper bounds on multiplicative matchings in groups, which rules out certain families of groups from this framework from proving omega equals 2. And in some cases, like in the capset type cases, it's known that slice rank actually proves like an optimal upper bound, asymptotically optimal upper bound on the size of multiplicative or additive matchings in certain groups. And so this raises a question, which was a conjecture of Petrov, if slice rank always proves an optimal upper bound on the size of matchings in groups. And I will mention a counterexample to that in the second part of the talk. Okay, so so just start with some background. As usual, omega is the exponent of matrix multiplication. I'll denote by n and n, the n by n matrix multiplication tensor, which I will just view as a trilinear form in 3 sets of variables: x variables, y variables, z variables. And the reason why I'm talking about this here is that Strauss showed that omega is the limit is n goes to infinity of log base n of the rank of this matrix multiplication tensor. Where here by rank, I just mean the normal tensor rank. So writing this tensor is a sum of product of linear forms in the 3 sets of variables. Okay, and the way that the main current approaches to giving upper bounds on omega work is by bounding the rank of n and n by using some auxiliary tensor whose rank you know, or whose rank you know something about. And I mean, this raises a question of like, what's an interesting family of tensors that you can say something about their ranks? And so Cohn and Umans sort of gave, there's one possible set of such tensors you could consider. And these are the multiplication tensors of finite groups. So if we have a finite group G, I'll denote throughout the talk T sub G as the bilinear map that takes 2 elements of the group algebra, say for now with the complex numbers, and multiplies them. Okay. So in coordinates, we'll often think about this like written out as follows. So it's the sum over pairs of group elements G and H of some x sub G variable times some y sub H variable times some z sub GH variable. Okay, and what do we know about its rank? Well, thanks to representation theory, we know that this group algebra is isomorphic to a direct sum of matrix algebras. So in some other basis, this T sub G tensor would have just been a direct sum of matrix multiplication tensors. And so we know that the rank of T sub G is going to be at most the rank of this direct sum, which is at most the rank of the sum of these, the sum of the ranks of these matrix multiplication tensors. And okay, so now the idea is that you take this tensor T sub G, like written in coordinates here, and you're just going to set variables equal to 0. So that the thing you get is a matrix multiplication tensor. And then the idea is that you will have shown that the rank of some matrix multiplication tensor is bounded by the ranks of some other matrix multiplication tensors, and you'll hopefully get some kind of recursive bound on omega. And in fact, this works. So the main theorem in this group theoretic approach is the following. So if you have this condition will appear throughout the talk, so I'm going to write it on the board. If there exists 3 subsets, S, T, and U of G, such that, so you look at this equation. Okay, so you look at the equation S times S prime inverse times T prime inverse times U prime inverse for S and S prime, and S, and T prime, and T, and U prime, and U. And well, there are always some like trivial solutions to this equation, namely if S equals S prime, T equals T prime, and U equals U prime. And if these are the only solutions to this equation, we'll say that S, T, and U satisfy the triple product property, which I'll just run it right. It's the TPP for brevity. Okay. So if this happens, if you have 3 subsets satisfying this condition, then you get the following bound on omega. Don't worry too much about it. It won't really come. This won't come up exactly, but so the geometric mean of the size of these sets S, T, and U to the power of omega is going to be at most the sum of the di's to the omega, where the di's are the dimensions of the irreducible representations. And so, I mean, the idea is that if this condition is met, then by zeroing out all of the x variables except for, so you basically look at the subcube of this tensor in coordinates here, where you look at the x variables of the form x sub st inverse with s and s and t, and y tu inverse with t and z u s inverse. So you look at the subcube, and that will be a matrix multiplication tensor. Okay, so that's how you realize matrix multiplication. Okay, and to get something useful from this, we will want to show that there are sets with whose satisfying this condition, whose geometric mean is large. So I will write TPP of G to be the maximum geometric mean of three subsets ST and U of G satisfying this condition. I should finish writing that condition. And so you can basically ignore the actual equation that gives you a bound on omega. So in this talk, so there's a simple necessary condition that comes out of that equation, which is that if you had a family of groups that proved omega equals 2, then this quantity TPP of G has to be at least the square root of the G to the 1/2 minus little o of 1. Okay, so this is a simple necessary condition for omega equals 2. So a simple consequence of this triple product property is that the product map from S cross T inverse into G, it just takes S and T inverse to S times T inverse, has to be injective, just because if you had multiple things whose product was the same, you would violate this condition. And so the size of S times the size of T is always going to be at most the size of G. And similarly for any other pair of these sets. And so this implies by multiplying and taking some roots that TPP of G is always going to be at most the size of G to the 1/2. Okay, so we want it to be at least the size of G, the 1/2 minus the low of 1, as always at most this. Now you might ask, like, how close to this can you get? Just as a very basic question, can you, for instance, have TPP of G being at least square root of the size of G over 100 for all large G? Turns out this is not possible. This follows from a removal lemma in groups due to Kral, Sarah, and Dana. So for any fixed epsilon for all sufficiently large groups G, this TPP of G will be bounded away. It is going to be at most like epsilon times the square root of the size of the group. Now, so basically all the non-trivial constructions that are known in this framework take place inside groups G that are semi-direct products of the integers mod m to the n with the symmetric group. And here n is going to be some small fixed constant like 8 or 7, and n is going to be going to infinity. Okay, and these kinds of constructions, it's a very particular kind of construction in groups of this form, which are called, I guess, simultaneous triple product property constructions. But in particular, these give triple product property constructions. And it's known that these specific kinds of constructions in these groups cannot yield omega equals 2. And like the kind of big question is, are there any families of groups that can yield omega equals 2? And it seems like we're not close to being able to answer this. But like one natural place to look is the family of simple groups. And so it's not too hard to show what simple groups are there. Well, they're cyclic groups, but it's not too hard to show that abelian groups can't yield any non-trivial bounds on omega. They're like the exceptional groups, but there are finitely many. So you won't prove a bound of omega equals 2.
Because you need like
you need an infinite sequence, yeah. And There are like the alternating or symmetric groups. There are very specific barriers known in these kinds of groups, but still, yeah, not much is actually known in these. But today I'm going to be mostly focusing on groups of Lie type, which are like one of the big family of finite simple groups. Example to keep in mind, SLN-FP. And here, yeah, so when I see groups of Lie type, I include groups that are like not necessarily simple, but are almost simple also. Basically, this is anything that people call a group of Lie type is included in what I mean when I say this. Okay. Okay, so there's this triple product property condition, and it seems like not too much is really known about it. So in this talk, we'll consider like two much weaker conditions that you might want subsets of a group to satisfy. One is that the subsets S, T, and U are product free. And this just means that the product of anything in S and anything in T is not equal to anything in U. Okay, and we'll denote independent in-depth of G as the maximum geometric mean of sets S, T, and U that are product free. And so it's actually a conjecture of Babai and Stosh that for some constant C, all groups G have a product free subset of size at least C times the size of G. And this is true for abelian groups. It's not too hard to show, but it turns out to be very false for non-abelian groups. So Gowers showed that, for example, the group PSL2P has no product-free subset of size larger than the size of the group to some power, specifically the size of PSL2P to the power of 8/9. Okay, so
TPP implies product free.
yeah, I'll mention that in the next very shortly. I'll give more details. Another condition, which is what's behind previous barriers for this approach, is out of a multiplicative matching, or I'll just probably say matching in a group G. So here we have three sets S, T, and U, which are going to be indexed sets, all of the same size n. Then we say that they are a multiplicative matching if the equation SI times TJ equals UK only has solutions if and only if I equals J equals K. And we'll denote max G as the largest such n, the largest size of such a matchings. And studying multiplicative matchings in groups is very closely related to questions about three-term arithmetic progression-free sets, say in the integers or in other abelian groups. And you can kind of think of a multiplicative matching as like an off-diagonal and possibly non-abelian three-term arithmetic progression-free set. So yeah, this bounds on match of G are, this is like proving bounds on some slight variant of the capset problem, and yeah, I mean, so for example, like there, I'll talk about some bounds later on this. But the idea is that the triple product property is stronger than either of these conditions. So it implies, so if you have a large set satisfying this condition, a triple product property, that implies the existence of large matchings. It also implies the existence of large product-free subsets. All right, so now I'll talk about some barriers. So what we showed is that for some epsilon greater than 0, no group of Lie type can yield a bound on omega better than 2 plus epsilon. And the main lemma behind this is the following. So if you have three sets, ST and U satisfying this condition, then this TPP, then the geometric mean of their sizes is going to be at most the square root of the size of the group divided by the second smallest dimension of an irreducible representation of G to the power of 1/6, plus some smaller order term. It's G to the 1/3, that doesn't matter. And if you're familiar with this work on quasi-random groups of Gowers, you'll probably be heavily reminded of, you'll probably, this will look very familiar. So let me sketch why this is true in some cases.
So what is meant by second smallest dimension? So the smallest dimension is 1.
The smallest
that number be 1.
The smallest dimension is 1. Now, the second smallest dimension is always going to be greater than 1. So I'm going to always only consider non-abelian groups. So basically, I mean, in the work of Gowers, the quantity that's considered is like the smallest dimension of a non-trivial irreducible representation, which might be 1. Here, this quantity min dim not equal to 1 of G is always going to be greater than 1. So basically, you skip all the one-dimensional things and look at the next highest. So let me show you using some result of Gowers as black box why this is true. So yeah, the main observation is that like this triple product. Yeah,
I lost it. Could you go back and just display the thing?
Yeah.
So what do we have to keep in mind now? So it's smaller than.
So that one condition which would rule out a family of groups would be if this min dim not equal to 1 of G grows as a polynomial in the size of the group. So this is at least G to the epsilon, for example. Then this is always going to be bounded like at most the size of G to the 1/2 minus some constant, epsilon to the 1/6, epsilon over 6. So the idea is if min dim of G is big, and this rules out things. Okay, so the reason, so why should you think this is true? Well, the idea is that if you have three subsets satisfying this condition, then within them you can find a product-free set of basically the same size. And this is also basically equivalent to saying that the matrix multiplication tensor contains a large subcube of zeros. Like it contains subcubes of like a quarter of the volume of the whole matrix multiplication tensor that are just filled with zeros. And this is like a very not random condition. This is not what you would expect randomly. Okay, so suppose we have three subsets satisfying this condition, well, then you can just like cycle the equation and write it as S prime inverse times T prime inverse times U times U prime inverse times S equals 1, if and only if this holds. And now just partition T into two parts of basically the same size. And then the sets S inverse times T1, T2 inverse times U, and U inverse times S are going to be product free if S, T, and U satisfy this triple product property. Just because T and T1 is never equal to T2 and T2. Okay, and that shows that the size of the largest product-free subset of G is going to be at least the geometric mean of these sizes squared, and maybe divided by a constant. And so what you get is that TPP of G is going to be bounded by some constant times in depth of G to the 1/2. And so now, for example, if you consider when G is, say, PSL2P, we have that like TPP of PSL2P is at most some big O of, well, in depth of G to the 1/2, which is the size of PSL2P to the 8/9 times 1/2, which is the size of PSL2P, to the 4/9, which is the size of PSL2P, to the something less than 1/2. Okay, so you can't prove omega equals 2 using PSL2P, for example.
8/9, you know.
So the 8/9 comes from the Scour's thing. Yeah. And more generally, this argument works. This argument works just using this thing of Gowers whenever the dimension of all non-trivial EREPs is at least the size of G to the epsilon for some fixed epsilon. For PSL2P, the epsilon happens to be like 1/3, which is, I think, the biggest epsilon that's known. But
Actually, you don't see where is this used, this condition now.
It's used in the proof of the Gowers thing.
Sure.
It's used basically if you unpack the proof of this result of Gowers. Basically, any group where the smallest non-trivial EREP is big will have no large product free subsets. And I'm going to sort of go through the proof of that now. Maybe quickly. Yeah, so why does this not just give us our theorem? This doesn't so our theorem is that any group of Lie type cannot prove something better than 2 plus epsilon as bound on omega. This doesn't just imply this because, well, one reason is that this only works for simple. So basically, this argument works for simple groups of Lie type of bounded rank. And our theorem applies to groups which are not necessarily simple, like SLN. And it also applies to groups which are not families of groups which are not quasi-random in the sense of Gowers. So, for example, groups like SLN3, where n is going to infinity. So this family of groups does have large product free subsets, but it cannot work. It cannot be used to give a good bound on omega. Okay, now I'm going to go kind of quickly through the actual proof of this main lemma. And this just uses some non-abelian Fourier analysis. But if you haven't seen this before, it might be a little too fast. So, but I just wanted to sort of show where this differs from the proof of this result of Gowers, if you're familiar with that. So the idea is you look at the indicator functions on these 3 subsets, S, T, and U in the group algebra. And then you look at, you basically write this condition as in terms of some convolution in the group algebra. So you write, let F be the function that's the 6-fold convolution of the indicator functions on these sets, S, S prime, S, S prime, T, T prime, and U, U prime. And then the observation is that this triple product property is satisfied if and only if the value of F at the identity is equal to the size of S times the size of T times the size of U. Okay, and that's just by definition of this triple product property. And then what you do, so this is all kind of standard, this is all very standard stuff in like non-abelian Fourier analysis. What you do is you write the value of F at the identity using Fourier inversion. So if the triple product property holds, it's equal to the size of S times the size of T times the size of U. But on the other hand, we can also write this as a sum over all of the irreducible representations of G, pi of the dimension of pi times the trace of this 6-fold product in the 6-fold product. So here pi of S, where S is a set, just denotes the sum over all elements S of pi evaluated at S. Okay, so each of these pi of something terms are just some matrices. We take the product and take the trace, and yeah, we get the value of F at the identity by Fourier inversion. And then, so so what we do now is you first look at the contribution from the trivial EREP to the sum, and basically what you want to say is that the other EREPs can't contribute much to the sum at all, so that the value of f at 1 is going to be very close to the contribution from the trivial EREP. So if pi is the trivial irreducible representation, then you just get this term of the size of s times the size of t times the size of u squared. And then you plus some other stuff. So plus, let's see, plus, okay, that pi or d pi is strictly greater than 1. And then you can ask what happens when d pi is equal to 1. Well, in this case, since pi is just a one-dimensional representation, pi of s is just going to be a sum of some complex numbers, and pi of s inverse is just going to be the sum of their conjugates, which is just the conjugate of their sum. So pi of s times pi of s inverse is going to be a non-negative, some non-negative number, and you take a product of a bunch of these things, and you add them up, so you get something positive. So if we throw them away from the sum, you just get this inequality here. Okay, and then you apply. You want to now show that the magnitude of this thing is small, and you do that by using Cauchy-Schwarz first. So bound the trace of the product of these matrices in terms of the Frobenius norms. Here I also like cycled the trace. So now we bound this as we bound the magnitude of this remainder as with Cauchy-Schwarz, and then by Parseval's identity we can. So now we want to control like one of these terms here, pi of s inverse times t, and using Parseval's identity you can show that that's at most the square root of the size of s times the size of t times the size of the group divided by this quantity min dim not equal to 1 of g. Okay, and yeah, this min dim not equal to 1 of g is entering because we've thrown everything else away. Okay, so plugging that in, you get following inequality, and then you apply Cauchy-Schwarz, and then you apply Parseval again to bound these sums, and that's it. So then you get that this product of the sizes is going to be at most the size of the group to the 3/2 over the square root of min dim g plus the size of g, and you conclude by taking cube roots. Okay, so yeah, this argument shows that if you have any group of Lie type, a bounded rank. Okay, so it was shown by Landis-Zuri and Sietz that for any group of Lie type of bounded rank, min dim not equal to 1. Is there? Let's see. I'm just wondering about the time. Okay.
More than 20.
Okay. Yeah, so for any group of Lie type of bounded rank, this quantity is always going to be a polynomial in the size of the group. So you rule those groups out. Then for groups of unbounded rank, like SLN F2, it's not the case that this grows like a polynomial in the size of the group. But it turns out that if you actually look at the actual inequality that was shown by Cohn and Umans to upper bound omega, the irreducible representations. So the actual EREPs of these groups are, if you combine this fact with basically lower bounds on the size of the EREPs of this group, you can show that in this case you also can't get too close to omega equals 2. Okay, so basically the idea of like this argument is basically that the multiplication tensor for the group G can't look very random, and so now I'm going to talk about prior barriers, which kind of which show that this multiplication tensor T sub G can't be highly structured in an algebraic sense, meaning it has low slice rank. And yeah, sort of the idea here is that the matrix multiplication tensor has a large diagonal subcube. So n has a subcube, diagonal subcube of size n to the 2 minus the low of 1. This is not like an obvious thing. It follows from like Barron's construction or the existence of Salem-Spencer sets. But yeah, so if you had a group that you could embed a big matrix multiplication tensor in, then that would have to contain a large diagonal. So it would have to contain, I'm just saying that differently, a large multiplicative matching.
This is related to the subrank. Yeah. Art talks about this.
Yeah, it's like the combinatorial sub. Yeah, yeah. Okay, so now a requirement, like, so based on this, like a requirement to get omega equals 2 via this approach, and even via these simultaneous triple product property constructions, which I haven't mentioned, is that the size of the largest multiplicative matching in the group G should be very big. So the size of the group 10 to the power of 1 minus the below 1. So the goal to rule things out would be to show that match of G is small for certain groups. And the idea, so how are we going to bound match of G? Well, an idea which was, so it was heavily used in this work of Blasiak et al., which I mean built on work of Tau, which gave like a symmetric formulation of the solution to the capset problem. The idea is that you bound this quantity using the slice rank of this tensor. And so here the slice rank of the trilinear form T is 1 if T is the product of some linear function of one part of one set of variables times some bilinear function of the other set of variables. And the slice rank of T is at most R if it's a sum of R slice rank 1 tensors. Yep.
You mentioned the Baron construction, but that's not end of the Abelian setting, but you're not Abelian groups here. So is it best construction worse or maybe better?
So so I guess the statement, it's like the matrix multiplication tensor contains a large diagonal, right? So the way I think about it is that so the problem is basically the same as finding a graph. You basically want to find a graph where each edge is contained in a unique triangle, and you want to maximize the number of edges. And like the solution to this is a classical problem in extremal combinatorics, and the solution to this is done using Barron's construction, and the same thing basically works here. And the key fact is that the slice rank of a diagonal tensor is equal to like the size of the diagonal. And so the match of G is going to be at most the slice rank of this tensor T sub G. And I guess here I'm also using the fact that if like slice rank is not increasing as you set variables to 0. So the goal is to show that the slice rank of T sub G is small. And so Blasiak et al. Showed that if you have any prime P, then for some constant C sub P, which is strictly less than P, match of the group ZP to the N, think of N as growing, as well by what I just said, it's going to be at most the slice rank of this trilinear form. And this holds over any field, in particular over FP. And they showed that the slice rank is bounded by some constant times C sub P to the power of N. So you have exponentially small, they're all multiplicative matchings, and these groups have exponentially small density. Okay, and what's really cool is that this is actually an asymptotically sharp answer. So Kleinberg, Sarin, and Speyer showed that match of this group ZP to the N is also at least C sub P to the 1 minus the low of 1 times N, for the same constant C sub P. Okay, so I guess this motivated this conjecture in a paper of Petrov that if you take the tensor T sub G And you look at the minimum, its smallest slice rank, where you're minimizing over the characteristic of the field that you're computing its rank over. So this is always going to be at most.
So T sub G is like a 0, 1 then.
Yeah, yeah. So we basically conjectured the reverse inequality of what we saw previously, so that you can give so that match of G is always going to basically be at least the slice rank of T sub G times some smaller order factor. And so something I showed is that if you take, for example, the group PSL 2 FP, then match of G is at most like the size of the group to the 8/9. This is basically just this result of Gowers. However, the slice rank of this multiplication tensor is always linear in the size of the group. It's always at least the size of the group over 8 for in any characteristic L. So this conjecture is false. Okay, and so how do you show this? Well, the first part is to show that there are no large matchings, and the observation to show that, and basically this follows very quickly from the fact that there are no large product-free subsets of the group. Basically, if you have a matching, you will have a product-free subset of size like a third of the size of the matching. So you get some polynomial bound on match of G. And then, so now you want to say that in any characteristic L, this multiplication tensor for PSL for the group algebra of PSL 2 FP, we want to say the slice rank of this is big. So one easy case when we can do this is when the group algebra is semi-simple. So in this case, as I mentioned at the beginning of the talk, this tensor T sub G is going to just be a direct sum of matrix multiplication tensors, where the sum of the DI squareds is going to be equal to the size of the group, and it's known that the slice rank of the direct sum of matrix multiplication tensors is going to be equal to the sum of like the DIs, or I guess the DI squareds, if the tensors are DI, DI, DI. Now now we have to basically this polynomial method is interesting for proving upper bounds in the case when the characteristic is dividing the order of the group, in which case the group algebra will not be semi-simple. This argument doesn't work, but it turns out it's still true that the slice rank of the multiplication tensor is at least the sum of the squared dimensions of the irreducible representations of G. So we can still talk about the irreducible representations of G if it's not semi-simple. This sum, however, may not equal the size of G. It will be smaller. Okay, so suppose that L divides the size of the group. We're going to try to use this bound, and this bound can be very bad. So, for example, in like the cap set type problems, the groups are going to be P groups, and it turns out that such groups would only have one irreducible representation, namely the trivial one. So this quantity, the sum of these d pi's squared is just going to equal 1, which just tells you that slice rank is at least 1, which is not a great bound. But it turns out that if you look at the representation theory of this group and any characteristic, there are always many large irreps. So there are basically two cases to consider. One is when the characteristic of the field is equal to P. So the case of like defining characteristic, it's called. And in this case, it's a little easier to actually just say explicitly what the irreducible representations are, and then you can just do some counting and show that this sum of d pi squared is large. You have to do a little more work when in the case of cross characteristics, so when L does not divide So when L is not equal to P and L divides G. It turns out, maybe you're familiar with like normal semi-simple representation theory, where the number of EREPs is the number of conjugacy classes. It turns out that in general, if L divides the order of the group, the number of EREPs is going to be equal to the number of conjugacy classes of order coprime to L. So basically, you can count the number of EREPs by counting such conjugacy classes, and turns out there happen to be like omega p of them. And now, so before we were using this bound of lambda Zurian Seitz to show that over the complex numbers, dimensions of non-trivial EREPs or nonlinear EREPs are big, but it turns out that they were actually investigating this problem in the case of cross characteristic. So the same result shows that, for example, in PSL2 FP, over in any characteristic L dividing the order of the group, the smallest dimension of a non-trivial EREP is at least is like linear at P. And yeah, by combining these, you get the lower bound on the slice rank. Okay, now I want to finish with some problems that I kind of like a lot. The first one is consider the group PSL2FP to the power of n. And the question is, does this contain large multiplicative matchings? So by this quasi-randomness argument, so when n is fixed, the smallest dimension of a non-trivial EREP of this group is going to be some polynomial in the size of the group. So for fixed n, the answer is no. There's like a polynomial bound on the size of match of G. And on the other hand, if P is fixed and n is going to infinity, so you're just taking a direct powers of some fixed group, the answer is also no. So it was shown by Solin that the slice rank of any group multiplication tensor, basically the slice rank of powers of any fixed multiplication tensor, or the slice rank of the direct product of fixed group is going to be like very deficient. So one conjecture is that in all like regimes of n and p, such a bound holds. So the size of match of G is at most the size of G to some 0.99. Okay, this should be true. But yeah, another question is, you now consider the same group, PSL2FP to the n. Does it contain large product-free subsets? Okay, well, the answer is yes. This is just because if you have product-free triple sets, A, B, and C in a group G, then you can just take, if you want a product-free subset in the direct power, just take the three sets where you have A in the first component, B in the second component, or B in the component of the second thing, and C in the first component of the third thing, and just take the whole group and all the other factors. So this gives you huge product-free subsets. But these are like, so if you're trying to show that you can't satisfy this triple product property, so this is sort of the motivating problem for all of these questions. These are like really not close to looking like things that would satisfy the triple product property. So, so one question is like, is there some kind of structure theorem for product-free subsets of these groups? Like, are these actually, for example, are these the largest such product-free subsets, or do all large product-free subsets have to like overlap significantly with these? And recently there were similar results in this flavor proven for the alternating groups. So it's now known in the alternating groups what the largest product-free subsets look like. And finally, like in the second part of the talk, I showed there was this representation theory argument for why the slice rank of this multiplication tensor of PSL2P is large. And it was very like particular to the representation theory of the group. But one question is, does a quasi-randomness condition alone like automatically imply high slice rank? And this is a question you can, and sort of all the questions on this slide you can talk about for just instead of talking about groups, you can just talk about like hypergraph versions of these. And yeah, basically the question is, do like tripartite hypergraphs that are quasi-random in some sense have high slice rank? Okay. Yeah, that's it. It's,
Yeah, any last question? What's the notion of randomness?
yeah. So for hypergraphs, so basically, what you have a tripartite like hypergraph, and you want to say that okay, it has some edge density, like in the case of when this is like the multiplication coming from multiplication in a group. I guess the tripartite hypergraph, it'll like you have the three parts are the copies of the group, and there's an edge when the thing multiplies to one. So I guess you have like okay, 3n vertices, like edge density n squared or n squared edges, hyper edges, and you just want to say that in any large look at three large subsets of it's basically a discrepancy condition. Yeah, and it's basically analogous to what the discrepancy condition for like expander graphs is, but yeah. Now you can also, another way of thinking about it, or you can look at like a trilinear form associated with a hypergraph, which in like the case of groups is just going to be this multiplication tensor T sub G. And what you want to show is that, so there's like the notion of the second largest eigenvalue of a hypergraph of Freeman and Wigderson. And another basically equivalent quasi-randomness condition to this discrepancy thing is that this trilinear form, or you just have to subtract something off, but it has a small maximum over the like unit sphere. Just, yeah.
So when you prove this gap, right, you have the match, you have the slice rank. So you prove the slice rank is high. Is the subrank also high? Like, is it also a large diagonal, or
like a large combinatorial diagonal, or
or non-combinatorial?
No. So for like T sub G, where G is like PSL2. There won't be a large combinatorial diagonal. I mean, I guess there is a large diagonal if you change basis to a direct sum of matrix multiplication tensors. If you're allowed to do that, yeah. But
yeah. So that's stronger, right? That implies that the slice rank is.
yeah, but I guess. Yeah, I guess, and you're talking about like border, like subrank, I guess.
Yeah.
Okay, because I guess if it's non-border subrank, then there's like a 1 minus the low of 1 and the exponent. But
yeah, you mean for mixed multiplication.
Yeah.
But in your results, is the subrank also high, or do you not know? This lower bound on the slice rank, right? Is that not how it goes?
So like in any characteristic,
Yeah.
it should always be at least like the size of the group to the 1 minus the low of 1, because you can always get a big direct sum of matrix multiplication tensors, like a linear size direct sum of matrix multiplication tensors. But yeah.
But yeah, your proof doesn't imply that the subrank is high.
I'm not sure. Yeah. I mean, it shows that this thing is basically a big direct sum of. It's very close to being a direct sum of matrix multiplication tensors.
Yeah.
But I'm not sure from there if. Yeah.